All right, everybody, let's get started talking about chapter 1.2 in Griffiths. We're going to be talking about differential calculus here and the tools you need in order to do the math we're going to be doing later when we calculate stuff. So we'll talk about ordinary derivatives, we'll talk about the gradient, the Dell operator, the divergence concept, the curl, product rules, and second derivatives. So we start out talking about ordinary derivatives here in section 1.2.1, and if you have, let's say, some function, there we go, some function of x, the question is what does the derivative of the function f of x do for us? What does it tell us? The answer is that it tells us how rapidly the function varies when we change the argument x by a tiny amount dx, right? Hopefully this is some review, but if it's not, that's okay. So in other words, if we increment the x value by an infinitesimal amount dx, f will change by an amount df, where df is the proportionality factor. So in this case, you've got a function there that has it's not changing much, so its derivative will be small. This function is changing quite a bit, so its derivative will be large. The derivative df dx is the slope of the graph at the point where you plot f versus x. If I take the derivative of the function at that point, it'll tell me the rate of change of that, or the slope of it. So if I change my dx just a little bit, it's going to change my df by a little bit, or a lot of it. How much? By this much. Okay, so we multiply our little change dx by this proportionality factor, and it gives us the new value. And this is the relationship. If we change x a little bit, how does f change? And that's what the derivative tells us. So moving on to the gradient then, section 1.2.2, imagine if you have a function that's not just of f of x, but three variables. For example, the temperature at every point in the room. So there's going to be a value, a temperature, 68, 72, whatever degrees, but at every x, y, and z in the room. So we can write our function t, our temperature, that depends on three coordinates, x, y, and z. What does the derivative of this function look like? So we need to generalize our derivatives to a function of n variables. The derivative is supposed to tell us how fast the function varies. So if we move a little bit from some point, and as we know, heat rises. So if you go up in a room, the temperature should change quite a bit. It should go from cold to warmer. But if you move left to right or horizontally, it shouldn't move too much. So this derivative, whatever we're going to do, when we take the derivative of this temperature function, it's not going to be the same. It depends on where we're moving around. So it sounds like it could be or should be complicated, but it's actually very easy. If you want to take the derivative of some function which depends on x, y, and z, you can actually just take the derivative of the function with respect to just the x coordinate, add that to the derivative of the function with respect to y, and then add it to the derivative of the function with respect to z. So you take a derivative. If you take the derivative of x squared y dx, okay, this is a derivative, then you know this is 2xy. The derivative doesn't affect the y coordinate in there. Whereas if we took dx squared y, dy, then this is going to be x squared, because we're going to take it with respect to the y thing. And then we can add those together, and it would become 2xy plus x squared, and then plus 0 because there's no z dependence in our function. So that's just if we had a function of temperature that looked like x squared y. Okay, and we don't in this case, but that's an example of how you could use that. So we can rewrite this in dot product notation to say that our derivative of the function is the derivative of the function with respect to x in the x hat direction, plus the y component in the y hat direction, plus the z component in the z direction, and then dotted into the differential element dx, dy, dz, each in its own x hat, y hat, z hat. And what happens when you do that, you know that x dotted into x hat is 1, and then x dotted into y or z is 0. So what you end up getting at the end of this is just the same function that we had before. So this is a shorthand notation. If we want to talk about this operator, this derivative function on our temperature value, we can write it as this: del t is equal to, or defined as, the derivative of the scalar function with respect to just its x-coordinate. The result of that points in the x-hat direction, the result of this points in the y-hat direction, and the result of this points in the z-hat direction. Okay, so this dotted into this little dl element is allowing us to point or figure out how it's working when we point it. Okay, so del t is a vector quantity with three components. A vector has magnitude and direction. So the direction of the gradient points in the direction of the maximum function of t, the maximum increase of the function of t. So the magnitude of the gradient gives a slope or rate of increase along the maximum direction. So you can think of it as when you are standing on a hillside, and then you look around and you find where the slope is going steepest away from you. That is the direction. If I calculated the gradient at that point, at where I'm standing, it would point in the direction. The magnitude and the arrow would point in the direction. So its magnitude, it would have a value, but its x, y, and z components would be such to point in the direction of the steepest ascent at that point. So the direction is the gradient. The magnitude is how steep the ascent is, or the slope. Okay, so what if our what if del t is equal to 0? This is called a stationary point. This is the same thing. If the derivative of a function is 0, like a one-dimensional, you know the derivative is 0 at this point, that point, this point, that point, this point, that point, right? The derivative of the function is 0 there because it crosses through an inflection point. So same thing as if the gradient is 0. Now you're talking about a three-dimensional function. If the gradient is 0, or if the derivative of the scalar function, three-dimensional derivative, is 0, then that's called the stationary point of the function. It could be a local maximum. So you could have your function kind of going up and coming back down, and this is a three-dimensional kind of mountain. And right at the top of it could be the derivative is going to be 0. It could be at the bottom of a valley. It'll be 0. It could be at a hill or a pass. It's the same for the derivative of a one variable function. So here's an example here, example 1.3. Find the gradient of this function, r is equal to the square root of x squared plus y squared plus z squared, which is the magnitude of the position vector. And if we do that, we take the derivative with respect to r, our three-dimensional derivative, and that's defined as, so remember, del is equal to d dx x hat plus d dy y hat, and so on. So we're going to take this d dx and d dx x hat multiplying onto our r, or acting on our r value. And so this is going to be the derivative of that, which is, oops, I just went backwards. Okay, the derivative of that is, there we go. Come on. Oh, I can't erase it now. Uh-oh. Let's try again. Okay, there we go. So this is r is equal to, you can think of it this way, x squared plus y squared plus z squared to the half. Okay, and to take the derivative, then it's going to be a half times x squared plus y squared plus z squared to the minus a half. Okay, so that's how you get the 1/2 out front, and then this ends up going on the denominator, and then chain rule times 2x, so then you get the 2x on top, and then you just repeat that for each x, y, and z, and you get 3 x hat, y hat, z hat. So this means you have this value pointing in the x hat direction, this value pointing in the y hat direction, and this value pointing in the z hat direction. You group all your terms together, add these things together, and you get x plus y plus z over the square root. And this is just our hat. This is just it's pointing in the direction radially. It's pointing in the radial direction at every point x, y, and z, and then it has a length of 1. So it says, the question is, does this make sense? Well, it says that the distance from the origin increases most rapidly in the radial direction. and that its rate of increase in that direction is 1, which is just what you'd expect. And then I've got this, see if this works, I've got this diagram going on here that you can see what this function x, y, and z looks like. Okay, so you see that it's just arrows pointing out from the radial direction, and if I ignore the z direction, if we just look in one dimension, you see that radially the length of the vector, so it's pointing this way, so that's a value of 1, this one's a value of 2, that's a value of 3, so the further away you get, the longer the vector is getting because it's measuring how far away you are from the origin. And if we take the derivative of that, we get this function, x, y, z over x squared plus y squared plus z squared, which is our r hat vector. And again, you can see that it's the vectors are all the same length. They're all length 1, and they're all pointing radially away. And if I make this 0 again, you can see that how that's working. So that's what this function is telling us. It's giving us this such that the radial vector is getting longer as you move away from the position vector is getting longer as you get away from the origin, which makes sense. It's this long, that long, getting longer. And if you take the derivative, it's telling you how quickly that's changing. So it's just increasing by 1 as it goes along. Okay, so let's go back to there. All right, so moving on to the Dell operator. The gradient has the formal appearance of a vector. This is in LaTeX, it's called nabla, but it's Dell, and it's when you multiply a scalar t, you get this nabla on t gives you x hat plus y hat plus z hat. It's some vector with x and y components. The components are the derivative of the function, and you can factor out this t, take it from there and move it outside the parenthesis, and we can define what del is, what the del operator is, and it's just this derivative function, but it preserves these vector components. So that's called del. Del is a vector operator. That's what we call this thing. It's an object. It doesn't do anything until it's allowed to act on a function. So you can think of it as multiplying functions, but it's more than that. It's not the same as just multiplying. There's 3 ways to multiply a vector or things together. You can multiply a vector by a scalar, you can multiply a vector by another vector using the dot product, or you can multiply a vector by another vector via the cross product. And we can do the same thing with del. We can act del on a scalar function, which is called the gradient, and this means t could be something like y squared plus 2x plus zy, something like that. That's a scalar because there's no x hat, y hat, z hat on it. So I can take the derivative of this and it will give me a vector because I'll get 2x hat plus 2y plus z y hat plus y z hat, something like that. I think I did that right. But that the original t is a scalar function, even though it's a function of x, y, and z. It doesn't have vector components. Or we can take the del and act it on a vector by taking the dot product, or we can take del and cross it into a vector. So this is called the gradient, this is called the divergence, and this is called the curl. So if you take del and you act on a scalar with it, then the result is an operation called the gradient. If you take del and you dot it into a vector, the operation is called the divergence. That's what you're calculating. And then the derivative crossed into, or the del operator crossed into a vector, gives you the curl. So remember, this is a derivative function. It's an operator that takes the derivative. So you're measuring sort of the rate of change of your function this way. You're measuring the rate of divergence of your function, and this you're measuring the rate of the curl, or the change around the swirl of something. And we're going to talk about those in detail now. So the divergence is defined as del dot v. What is del? It's this derivative operator. And what is a vector? If not just components in an x direction, components in a y, and components in a z direction. So this is the x component of v, in the x hat direction plus the v hat component, y hat component, plus the z hat component. If we multiply that together, then it's just the derivative of the x hat dotted in the x hat gives you 1, and the off terms give you 0. So your result, del dot v, is just you take the derivative of your vector x component with respect to x, derivative of the y component with respect to y, and derivative of the z component with respect to z. Notice that this is a scalar. So if I take del dot v, I just get a number. I just get a number. There's no vector components on these. They just add up. I get a number plus a number plus a number. It could have, this could be, you know, x squared plus y plus z or something, no vector components, but then when I plug in my position at some x, y, and z coordinate, 0, 0, 0, or 1, 2, 1, or whatever, I get a number out of it, and that number is called the divergence. It's a measure of how much the vector v spreads out or diverges from a point, x, y, and z. This is an example. If you have a function that looks like this, we call that, it's got a positive divergence. This function here has 0 divergence, and this function here also has positive divergence because it's changing as a function of distance as you move away. Whereas this one, 0 divergence because it's constant from through all space, it appears to be. Okay, so we got an example here. Example 1.4, it says suppose the functions that I just showed you are this one, which is actually the one we looked at on Math 3D, just x plus y plus z, and then wants us to calculate the divergence of that. So we take the derivative with respect to x, with respect to y, with respect to z of the x hat, y hat, and z hat components. And so the x hat component is just x, the y hat component is just y, and the z hat component is just z. The derivative of x with respect to x is 1, so you get 1 plus 1 plus 1, 3. So the divergence of this guy here is 3. Okay? If you look at the second function here, and let's say that that function is just z hat, okay, let's take the derivative of that. Derivative of the x component is 0. Derivative of the y component is 0 because there is no x or y component. Derivative of the z component is the value vb equals z hat. It's just a value of 1 all the time, so you just get 0. So no divergence. The other one is a function, it depends on z, so it's z hat, so it's not just a number 1, it's just z hat. So the derivative of z is 1, and that gives you 1 here, so that's a positive divergence. So that's how you calculate the divergence of a vector field, for example. And then you got some other problems here that you'll do in your assignment. Okay, so now let's talk about the curl. So we're talking about all the ways we can take del and act on vectors. So we did del times a scalar function, or acting on a scalar function. We do del dot a vector, and now we're going to do del cross another vector. So del cross v, we set up our cross product where we've got our x hat, y hat, z hat. Our del function is d dx, d dy, d dz. And then our x component, our v component, is vx, vy, vz, our vector. And you get this mess, and that's just I should fix that. 1.2.5. So the geometrical interpretation of the curl is just a measure of how much the vector swirls around a point in question. So if you have a vector field that looks like this, that's going to have a curl. This is also going to have a curl because it's longer further away, and then they get shorter as you go in, so it's swirling around this point. They're going up and then down and up and down. So example 1.5 is, say that this function here is minus y x hat plus x y hat, and then the figure over here is just x y hat, and want us to calculate their curls. So you plug in d dx, d dy, d dz, and then we know that our vector only has x and y hat components. You put that in here, and you can take the derivative of that minus the derivative of that, and you get 2z hat, okay, and the derivative of this on that, and so on, okay, in the z hat direction. And then this one, you do the same thing. d dx x is 1 in the z hat direction, and that gives you z hat. Okay, so as expected, they both have curls in the positive z direction. So why are they in the positive z direction? Right hand rule. So that figure A, you swirl your hands around in the direction of the swirl, and your thumb points in the direction of the curl. Okay, so that curl has a magnitude and a direction. So the magnitude tells you how much it's swirling, and then your thumb points in the direction perpendicular to the swirl. Okay. All right. So then product rules. So there's divergence and curl and gradients. Those are all really important functions. You have to make sure you really understand what they're doing. Okay, so the calculation of ordinary derivatives is facilitated by a number of rules, such as the sum rule. The derivative of the sum of two functions is just the sum of the derivatives. The rule for multiplying by a constant, the constant can come out. The product rule, first derivative of the second plus second derivative of the first. The quotient rule. You can have the same types of relationships for vector derivatives. Do the same thing, multiplication, you can distribute it through. Del cross A plus B is del cross A plus del cross B. And then you've got multiplied by a scalar. You've got this and that and so on. But then there are two ways to construct a scalar as the product of two functions. If you multiply two scalar functions together, you get a scalar. If you dot two vector functions together, you also get a scalar. And then there's two ways to make a vector. If you take a scalar function and multiply by a vector function, you will get a vector function. And if you cross two vector functions, you'll get a vector at the end of the day. Accordingly, then, there are 6 product rules, 2 for gradients, okay, which is this one, first derivative of the second plus second derivative of the first. But then there's this one. Instead of multiplying by scalars, we've got to dot products and then do del on that. We're going to do del on the result of this dot product and this big mess here that you can look up at the front of your book if you want. And then for divergences, you have the same thing, a scalar times a vector, del dot just a vector. You can pull that function out and then do del dot a plus a dot del dot f, and then you've got another one here, del dotted into a cross b is equal to b times del cross a minus a dotted into del cross b, and then 2 for curls, same thing. So you just have these identities here if you're doing, if you have the derivative of products, okay? So anytime you have 2 products, scalar functions and vector functions, and then you're going to take a derivative of that, make sure you're paying attention to the product rules. Generally, we don't have to interact with this too often, but it's important to be aware of. Okay, and then there's quotient rules, which, you know, bottom derivative of the top minus top derivative of the bottom, all over bottom squared. Okay, so those are product rules, and again, you'll just have to be aware of those rules. Sometimes you will need to use them. Second derivatives, 1.27. Oh, God, I didn't fix that. So, div, grad, curl are only using the first derivatives first derivatives using del. We can apply del twice in a row, though, and take second derivatives. And there are 5 species of second derivatives, and I need to fix that. It should be 1.27, 1.2.7 second derivatives. So the 5 species, since the gradient del t is a vector, we can take the divergence and curl of it. So we can do del dot del t, or we could do del cross del t, because the result of del t is a vector. So we can take the dot product of a vector or the cross product of a vector. We can also take the divergence, we can take the gradient of a divergence because del dot v is a scalar, so we can take the derivative of that function. And then curl del cross v is a vector, so we can take its divergence and curl too. So we can do del dot del cross v or del cross v. The first one, del dot del t, this is what del t is, and then we're going to dot that into del again, and it just looks like what you'd expect. It's the second derivative of the function. D, you just take 2 derivatives in the x direction, 2 derivatives in the y, and so on, of the x component. This object, this is the most important thing you're going to deal with in this class so far, is called the Laplacian. And the Laplacian is written as del squared for short, del squared on the object for short. The Laplacian of a scalar is a scalar, okay? So that's an important thing. You can also have the Laplacian of a vector, and so if I do del squared on a vector, then you get this, and it's the second derivative of the x component in the x hat, y hat, and z hat, so you just end up with a vector. The curl of a gradient, number 2 out of these 5, number 2, the curl of a gradient is always 0. Del cross del t is always 0. That's an important thing. Make sure you write that down and get comfortable with that. Number 3, we rarely do this. It's just the gradient of the divergence, so we don't worry about it too much. The divergence of a curl, like the curl of a gradient, is always 0. So these are your 2 lifesavers. A lot of times you'll encounter these and you can just go boom, gone, I don't even have to calculate it, okay? So del cross del t is 0 and del dot del cross v is 0. And you can prove this for yourself. And then there's this last one, del cross v is equal to del times del dot v minus del squared v. And then this del dot v is number 3 and del squared v is just a little Laplacian. So at the end of the day, the only ones you care about, there's only really 2 kinds. That's the Laplacian and then the gradient of the divergence, which we rarely encounter. So we don't really need to worry about going into third derivatives. Okay, and that's all I have. That's section 1.2, and that should get you started on the assignment. Okay, see you guys later.